welcome to The Explainer. Today, we're talking about something really special, one of the most powerful tools in all of astronomy. It's a single chart that, get this, unlocked the entire life story of the stars.
You know, when you look up at the night sky, it's easy to think of it as this timeless, unchanging picture. But those little points of light, they're not static at all. Every single one is on its own cosmic journey. It has a birth, a life, and, eventually, a death. And for centuries, that journey was a total mystery. I mean, think about it. How could we possibly understand the life of something that lives for billions of years? It seems impossible, right? Well, the answer came from this revolutionary map. But here's the cool part. It wasn't a map of where stars are in space, it was a map of their journey through time.
Okay, so let's dive right in. This incredible tool is called the Hertzsprung-Russell diagram.
So what is it, really? Well, at its core, it's just a scatter plot, a graph. But instead of plotting, something like height versus weight for people, it plots a star's true brightness, what we call its luminosity, against its surface temperature. I love this analogy. Think of it like a giant family portrait of the stars. It organizes them all based on what they're really like, their most fundamental properties.
And right away, this chart shows you something incredible. Its first big revelation. When you start plotting thousands and thousands of stars, they don't just land randomly all over the place. Nope, they fall into these clear, distinct groups. And that was the very first clue that the universe of stars, which looks so chaotic, actually follows some very specific, very predictable rules.
Okay, but to really get what those rules are, you've got to know how to read this map first, and it all comes down to understanding the axes.
So, on the vertical axis, that's luminosity. The super bright, powerful stars are way up at the top, and the dimmer ones are down at the bottom. Simple enough. Now, the horizontal axis, that's surface temperature. But here's where it gets a little weird. It runs backwards. The hottest stars are on the left, and the cooler ones are on the right. It's just a historical thing, a convention that actually helps it line up better with what astronomers see through their telescopes.
And speaking of what astronomers see, they actually use two main versions of this diagram. There's the observational one, which plots exactly what we can see from Earth through a telescope, a star's color and how bright it looks to us. But then there's the theoretical one, which plots the star's true physical properties, its actual temperature and how much energy it's really putting out. And trust me, converting between what we see and what's actually happening out there can be pretty tricky. It really shows you that crucial link between just looking at the sky and truly understanding the physics behind it.
All right, so we know how to read the map. Now let's do it. Let's see what happens when we actually plot thousands of stars on it. This is where the story really starts to come alive, in what we call these stellar neighborhoods. And like we said, it's not just a random mess of dots. We see these very clear groupings. In fact, most stars fall into one of four main categories. You've got the main sequence, the red giants, the supergiants, and the white dwarfs.
The first thing you notice, the most dominant feature by a long shot, is this big diagonal band. It runs from the top left all the way down to the bottom right. That's the main sequence. And get this, it's home to something like 90% of all stars, including our sun.
Think of these as stars in the prime of their life. This is their stable adult phase, just steadily burning through their fuel, fusing hydrogen into helium in their cores. The really hot, bright, massive ones, they hang out up in the top left, and the cooler, dimmer, less massive stars live down in the bottom right. And really, where a star lives on this street is almost entirely decided by just one thing, its mass.
Okay, now look up above the main sequence. Up there, you find the giants and the supergiants. Now, these stars are pretty cool temperature-wise, which is why they look reddish, but they are incredibly bright. So, how is that possible? Well, it's because they're enormous. These are stars in their retirement phase, you could say. They've run out of their main fuel and have just puffed up to hundreds of times their original size.
And finally, down in the bottom left corner, that's the stellar graveyard. This is where the white dwarfs live. These are the leftover cores of dead stars, what's left after a star like our sun dies. They're super, super hot, but they are tiny. We're talking about the size of Earth. So even though they're hot, they don't put out much light overall. They're basically the smoldering embers of a star that's gone out. But here's the most important part. These neighborhoods, they're not separate places. They are stops on a single journey. And that is the real power of the HR diagram. It's not just a snapshot. It lets us map a star's entire life. It shows us the path it's going to take.
So, by just looking at this chart, we can literally trace a star's life story.
Take a star like our Sun. It spends most of its life, about 10 billion years, just hanging out on the main sequence. Then, as it gets old, its dot on the map moves up into that red giant neighborhood, and finally it blows off its outer layers and its core collapses down, becoming a white dwarf, destined to just cool and fade away for trillions of years.
You have to understand how revolutionary this was. Before this diagram, the best theory anyone had was that stars got their energy just from collapsing under their own gravity. But that model meant the sun could only be a few tens of millions of years old. And that created a huge problem. Geologists and biologists were looking at rocks and fossils and saying, no way, the Earth is way, way older than that. And this is where the HR diagram became the smoking gun. A physicist named Arthur Eddington looked at that long, stable main sequence and had this aha moment. He realized that gravity just couldn't power a star for that long. There had to be something else. And he proposed it. The true power source was nuclear fusion, the smashing of hydrogen into helium. It unlocked a mind-boggling amount of energy, and just like that, it solved the age paradox overnight.
And what's really amazing to me is that even now, over 100 years later, this map is still one of the most important tools astronomers have.
I mean, its creation was a real team effort, building on these huge star surveys from Harvard. But the chart itself was independently put together by two guys, Hertzsprung in 1911 and then Henry Norris Russell in 1913. It wasn't until a bit later that Eddington came along and gave everyone the stunning physics that explained why it worked. And today, it has some really powerful practical uses. For example, astronomers use it to measure cosmic distances. It's a clever trick called main sequence fitting. They basically look at a star cluster, see how bright its main sequence appears to be, and then they compare that to a main sequence they already know the distance to. By seeing the difference in brightness, they can calculate just how far away that new cluster is. It's like a cosmic ruler. It's ingenious.
And it's not done. It's still revealing new secrets. Just recently, data from the Gaia satellite showed us that the story of dying stars is even more complex than we thought. It turns out that white dwarfs, those stellar embers, don't all cool down the same way. There are actually two different cooling paths they can take, and it probably has to do with what their atmospheres are made of. How cool is that?
So all of this just goes to show you, the HR diagram is not some dusty old chart in a history book. It is a living, breathing tool that's still evolving, still challenging what we know about the universe. It's what took stars from being just little points of light and turned them into characters in this grand cosmic drama.
Yeah, the Hertzsprung-Russell diagram gave us the story of the stars, a story written in the language of light and heat. It mapped out their past, their present, and their future. And it leaves us with this really exciting question, doesn't it? What other incredible cosmic stories are just out there, waiting for someone to draw the right map to reveal them?